happy to welcome parents to Parents Weekend, Family Weekend here at Carnegie Mellon University. I should say, first of all, we're really here to thank you for letting us have the pleasure of working with your students, working with your kids. I will say that I chose to become a professor primarily because it meant that I got to meet and work with some of the brightest people who will help to push the next generation forward. And that makes you happy about the future. You know, in light of all things that are happening in the world, you know, my son the other day, we were talking about something about the future, and he said, "Oh yeah, we all learned that in 11 years the world will end." That's a middle school kid. Okay, anyway, but I'm just trying to say, in view of all of these things, it's nice to know that there are some people who are maybe going to be capable of pushing this all forward. And for me, working here at Carnegie Mellon and working with some of your students definitely gives me that feeling every single day. A little bit about what I do. I'm a math professor. Math is, at first glance, about as far away from something that's directly applicable as you could imagine. But however, I'd say that here at Carnegie Mellon, a lot of the attitude towards math is not only math for its own sake, but math for other sakes. So in that regard, I actually have students in my classes who are not only math majors, also studying computer science, or music, or anything else, business, engineering, and so on. Now, I think that a common thread for all of the students that are here is that generally Carnegie Mellon students like to work hard. And I will say I thank you for letting us have students who want to work hard to take our classes, because it makes it so much more fun to teach a class when you can say, what's the interesting thing I can teach? Where interesting means something pretty challenging, something that's intellectually stimulating for the person teaching it. And we get to make those decisions. In fact, that's how I architect all of my classes. I teach a class that is taken in spring, every other spring, by all of the math majors at Carnegie Mellon, freshman math majors, sophomore math majors, and so on. And it's called discrete mathematics, which is the math that's actually behind computer science. The way I teach my class, the way I organize my class, is I go and grab a book about discrete mathematics, and that's not the textbook for the course, because it won't work. The level of Carnegie Mellon students is quite high. So I just look at the table of contents and say, what are the most interesting things you can teach about each one of these topics? And none of those are in this book, because they're too interesting. But that's what the entire course is. And in the course of this, everyone learns all of the basic stuff as well. Now, another class that I teach at Carnegie Mellon is called the Putnam Seminar. The Putnam is a mathematics competition that college students participate in. In fact, I know that at least some of the parents in this room have their students in this class with me. This is a very unique competition. It's actually sometimes called the hardest math competition in the world. And that's because it has 12 questions to be done over a period of 6 hours on a very, very bad day. The day is the first Saturday in December. This is historically always this way. It generally coincides with the Saturday before you have to study for all of your final exams. So this is only taken by crazy people, okay? This is a thing. Throughout the North America, United States and Canada, all the crazy people who are interested in taking this contest are allowed to. And it's also important to say something about what the typical scores are on this contest. You see, there are 12 questions, I said, and each question is worth 10 points. Every question is worth the same amount. So simple math, the total maximum score is 12 times 10, which is 120. And the median score, a measure of the average, the median score every year is about 1 point. I said each question is worth 10 points, and there are 12 questions, okay? So now you get an idea that if 5,000 people in the entire North America are trying this test, and the median score is 1 point, these are crazy people. I should say it's not always 1 point. The median score is a good measurement of the difficulty. On an easy year, the median score is 2 points. This is like how we empirically determine whether it's easy or hard. A hard year, the median is 0 points. Okay, so somehow the median is like 0, 1, or 2. Carnegie Mellon University, out of all North American universities, out of all universities that participate, has the largest number of students who participate in this contest. More than MIT, more than Harvard, and that's because Carnegie Mellon is full of crazy people. And I mean this in the best possible way. What I mean is, this is why I enjoy teaching here. I can say, okay, what's challenging? And okay, why are these students taking this thing? Are they trying to win? You don't have to. Life is not only about winning some contests. It's called a contest, but people aren't even taking it just to try to win the contest. They're taking it for the intellectual challenge of saying, can I beat the median score? And it's okay. Because if they don't succeed, they can just say, I was only 1 point away. Zero is only 1 away from 1. I always explain to them on the first day of this class that this only has upside. Because if you don't do well, it's not really that bad, and you just don't tell anyone you took it. If you do well, and you get some score in the top 500 in the North America, you put it on your resume. No, if you didn't get it, just don't write anything down. No one knows anything, right? And by the way, Carnegie Mellon has the second most students who make it into the top 500 of all North American universities. So that's the level. In case you didn't know what your students are in, your students are in a crazy place where there are a lot of other people who are pretty good at not just math, but I call this analytical thinking. I'm coming from the point of view of math because I'm a math professor, but we have students in that class who are not math majors. And what I really enjoy working here, is that there's so many people who use math in some way, and they somehow take this class and I get a chance to teach them something. I can't give a talk without talking about some math. So we're going to actually get into some math. And the problem I want to talk about is a problem that was inspired by one of these classes that I was teaching. So the way I teach this class, by the way, is that there are about 200 students at Carnegie Mellon who want to play, who want to try this thing. And most of them have never done serious math competitions in their life, because that's not the point. The point is to learn how to think. They just want to try to learn. Now, I break the class up into some different groups, which are just based on how much experience you have. The most crazy group works for 3.5 hours on every Sunday. They're crazy, and afterwards we go out to dinner and something. And over one dinner conversation, one of these students said, hey, have you heard of such and such problem? This is the sort of thing that happens. Faculty here learn from students also. Students say, I just learned something. And generally, if the faculty member, like me in that case, says, no, I didn't hear about this before, our response is, can you tell me more? Right? We want to learn also. I'll say I've learned a ton by teaching here from the students who are always telling me, did you know this? Did you know that? And so this came as a kind of a rough question. I've polished it over many years of giving this talk, and you'll get the diamond version of it. The diamond version of it is a game. Let me switch to a different screen here. I have some flashing thing here. Okay. You know what? Let me turn my computer into touch screen. One second. I need to make a touch screen. Where are we? Mac. Okay. There we are. That worked. Okay. Right. So I just froze this, and what this is it's a chessboard thing with 2 colors. I made my computer a touch screen so that I can show you that if I touch things, I change the color. It's quite reasonable. You can just touch a bunch of things, change a bunch of colors. If I said your job was to memorize this picture, is this doable? Actually, I've tried asking different audiences. If you ask me to memorize this picture, my answer would be no. No in the sense of, it's tedious and I don't know if I'll remember it and what's the point. I've actually given this talk in high schools. I'm shocked by how many high school students look at this and say, oh yeah, no problem, I can memorize this. Students these days seem to be able to remember all kinds of things. Okay, but if this seems reasonable, then I tell anyone who thinks this is reasonable, I have a different challenge for you. Oops, your challenge is this one. So does this seem reasonable to remember? No. There are very few sane humans who would say that this is a reasonable thing to remember. Actually, how much memory does it take to remember this? So as you know, I don't just work on math, I'm also interested in computer science. You can ask what's called an information theoretic question, which is, if I was a computer, how much memory, like the thing in the RAM, how much RAM would I need to store this? Well, that's actually calculatable. Every one of these squares is either red or not red. That's called 1 or 0. These are called bits. I know this is the math talk, but this is computer science. It's not that crazy. Every single one of these would take 1 bit in order to remember. And the number, simply, I heard someone say there are 256 squares, and that's because they're built in 8 plus 8. That's 16 across times 16 up and down, 256 squares. So you would need 256 bits of memory to remember this. You may know that computers don't measure memory in bits, they measure in bytes. Byte is 8 bits. That's just some historical reason for this. So it would take 256 divided by 8 which is 32 bytes of memory to remember this. When was the last time you saw a device which had on the label 32 bytes? Never. What's that? I don't even know if they made those. I don't even know if they bothered to make 32-byte memory modules, right? This is very, very, very small. Everything we use these days is like my phone, but like GB memory, right? G is giga, 10 to the power 9 billion. So actually, this takes almost no memory. But this is what I use as a demonstration to communicate that this is why memorization is pointless. You will not be able to beat a floppy disk, right? So that's actually what we try to do in math class here. We're not trying to teach anyone how to memorize anything. In fact, the whole point of our classes is to say, here's a problem. How do you think you can try to come up with a way to solve this problem? We want our students, when they graduate, to be able to look at arbitrary problems, not just math, like in any place, and not say, has my teacher taught me how to do that before so that I can do it now? No, we want everyone to be able to improvise and figure it out as we go. Now, I did talk a little bit about this, about memorizing something, so I want to give everyone still a challenge. I'm going to give you a picture of an 8x8 chessboard, and I'll give you 1 second to see how much you can memorize. Okay? 1 second. Is everyone ready? 3, 2, 1, start. Did anyone memorize that in 1 second? How come it only took you 1 second? I thought that this was hard. Well, it's not, because there's a pattern. So this is what human beings' brains are extremely good at. In some sense, what's the human brain for anyway? It's not for memorizing arbitrary, messy bits of data. It's not for remembering disorder. Actually, the human brain is a remarkable piece of equipment that identifies patterns. And what we're always trying to do is we're trying to match patterns and match concepts that we've seen before. And once you have the concepts, then somehow instantly you're able to do very rapid calculations. In fact, what you just did here, your brain was basically taking the visual cortex. It took all 64 of the squares, and in the blink of an eye, it matched it against a pattern of letters of the English alphabet. And bam, you've got it. Okay, so this is often what I use to share, like, somehow this is neat. And this is why what we should do is we should try to find patterns and methods to do things. And with that, I actually want to return back to the original challenge, because I actually want to play this challenge, but I want to play a slight variation of it. So I still want to be able to somehow play with arbitrary, messy things, but I'm going to change it into a game. The game's going to work like this. We're first going to invite an audience member to come forward. The audience member will get to mess around pressing a bunch of these things. Okay? Make it so that they feel it's really, really messy. When they're done, then I'm going to look at this, and in about 1 minute, I'm going to try to take it in. Then I'll look this way, close my eyes, and the audience member will change exactly 1 square. Change exactly 1 square means, change exactly 1 square. Actually, I should say, when they do it, for the audience to see what changed, it's probably easier for them not to use the touch screen. They can just move this mouse around, and when they're happy, they just click on the button and they change it, right? So they change 1 square. Then I'm going to turn back around, look at this, and I'll tell you what changed. Does the setup make sense? They get to start with whatever mess they want me to memorize. I'll spend about a minute, take it in, and then they get to change exactly 1 square. They must change 1 square. And I look back and I tell them which changed. How does the difficulty of this compare to memorizing the whole thing? Is it the same? It's not the same. I see someone shaking their head no. It's not the same, because you see, they touched that one. So this is why you need to remember to move the mouse. So when you see the person do this, so my eyes are closed. I cannot tell if people are moving the mouse or not. Your job, if you see the person do it and declare they're done, you have to yell at them, please move the mouse. This has happened before when I gave the talk. And I do hear someone say, please move the mouse. So this is why I always give this instruction. Or else you guys look at this and say, oh, come on, the guy didn't do anything. Okay? All right. So I actually want to demonstrate this. And of course, if you have some way of doing this, you get to play along too and see if your method works. Could I ask for a volunteer? Does anyone from the audience want to come up and help me mess around with this? I just need one volunteer. Yes, please come forward. Come forward. Okay, don't be shy. So come forward. And actually, it might be better just so you familiarize yourself with the touchpad and the button, not to use the touch screen.
Okay.
You can too, but this is how you move this around,
Okay.
and then that's the click.
So
But let's just like start making a mess. So that's actually why it's important. The making a mess part is important for two reasons. I'll make sure we give him time. It's first to make sure he's familiar with the equipment so that there's not a mistake on the second half. And the second reason is because you have no way of knowing that I didn't just have a few setup, like pre-memorized stuff, right? Even though it was flashing at the beginning, how do you know that those are actually random? There's actually a story behind this. I don't know if any of you have heard about this. In the 70s in the United States, there was a game show on TV. It had something called the Whammy. Has anyone heard this story before? Some people have heard this story. So there was a TV show, and it was something where, as part of the game, you got to press a buzzer thing as some random pattern was going on the screen, and then you'd get some prize, or maybe you'd get the chance to do it again. It looked random. Some guy living in his mom's basement watched enough reruns of it to find out there were only like 12 different things that flashed one after each other in cycle. So it looked random. He practiced, and then he started racking up tons and tons of money on live TV, causing the network executives to get go crazy as this guy's like making $100,000. Okay, meanwhile, you seem to have made a mess. That's good.
I'm good at that.
Okay, now I'm going to have to stare at this. Hang on a second. This actually takes some concentration. Okay. I got it half done, half done, half done. Okay? Okay. Please change exactly what.
Okay.
Did you move the mouse?
Yeah.
Okay. So now what I'm going to do is I'm going to click on something. I'm not saying I'm choosing this. I'm just going to press this because it'll help my calculations. I might guess it at the end. Let's see. Okay. I see that what you touched is in the bottom half of the board. What you touched is in these bottom 4 rows of the board. Okay. I see that it's in one of these 2 rows. What you've touched is in somewhere here or here, one of these 2 rows. What you touched is in the bottom row. You touched something in the bottom row, okay? Let's see. It's one of these 4. It's one of these 4 on the left. It's one of these 2. It's one of these 2. Okay. You touched this one?
Very well.
Okay, well thank you. That's all I need to know. So that was right? That's good, because I don't remember anything about the board. So something that's kind of fun about this. When I was closing my eyes, I was remembering one thing and one thing only. When I opened my eyes, touch that. Okay. But now, and I didn't know anything else about the entire board. But let's talk a little bit about what's behind this. First of all, let me return it to what it used to be before. These 2. I like to use this puzzle because it lets us even talk about, it's actually an application of math. It's called information theory. It's related to data compression. It's like every time you have a zip file, .zip file, I don't know if you know, it's smaller, magically. How is it smaller? You can't just go and take something and get smaller. I remember when I was a kid, I was like, why don't we just zip the zip file? You know what I mean? It's like, no. There's some limit here. So the interesting thing about this problem is, what's the minimum amount of memory that is required to actually execute the trick we just did? Right? Like there's a naive approach. Naive approach is called memorize the whole thing. You just need to then remember 64 bits. There are 64 little squares. If you can remember each of their red or not red states, then you'd be in good shape. So you can do this with 64 bits of memory. But you can do it with less. Does anyone have any ideas of how you could save memory? Meaning not remembering 64 zeros and ones, but remembering something else? Yeah.
I worked on this in the car on the way here.
So you were trying this, okay.
Even and odd, you can count even and odd rows. Like a row is either even or odd.
Okay.
And so.
Okay,
that's a
so
start.
this is a great start. And by the way, this is the kind of conversation we were having in this Putnam class. Like basically, students said this, and we started to try to figure out what interesting thing can you do. Actually, the student asked me a completely different question, but it somehow can be translated into this performable thing. So what you just said is one of the first ideas, which is called, if I could tell which row and which column was touched, I am done. How can I find out which row got touched? If you could remember each row's even or oddness of reds, you will find out which row's even or oddness of reds changed, right? So what I have to remember is the first row is what? Looks like it's odd. Okay, first row is odd number of reds. Oh, by the way, let me give you a trick. How did I know the first row has an odd number of reds? Actually, I didn't count the reds, I counted the grays. Because the reds plus the grays are 8. And the nice thing about 8 is 8's an even number. This is actually a little bit of number theory. If I have an even number called 8, the two things that add up to the 8 have the same evenness or oddness. They're either both even, adding up to 8, or they're both odd, adding up to 8. So whenever I want to know evenness or oddness in a row of reds, I can just look at the grays if there are less grays. Okay, so with this technique, you're going to remember odd. And the second row is even. And the third row is even, right? So you could do this. You can figure out all the even and odd. And then at the end, while your eyes are closed, somebody touches, well, I'll just touch this way, touches that one. And then when you check again, you find out the first one's still even, the first one's still odd, and so on, so on, so on. Oh, but the last row, it changed from odd to even. Therefore, you know for sure that something got touched down here. And you have consumed 8 bits of memory to find out which row got touched. Now, how do you figure out which column got touched? You do the same thing with the columns. So if for every column, you also are remembering the evenness or oddness of the column, let me undo that. If you're remembering the evenness or oddness of every column, then you can also know which column got touched. So it takes you 8 rows and 8 columns, which is 8 bits plus 8 bits, 16 bits, and you can do this whole thing. So that's now more efficient than 64. But it turns out you can do even better. You can do better. Does anyone have ideas of how you could reduce? Do you have another idea?
I don't want to.
Well,
I do.
You do?
But
Okay.
Introducing a third dimension, a third way of dividing it. So
Mhm.
what I do is quadrants.
Okay. So, you see, the thing we just did is we said that if you want to know where something is in in a two-dimensional array or a two-dimensional flat thing, if you tell it's vertical and it's horizontal, you know exactly where it is. His idea was to say, you see over here, I have 64 squares. 64 is not only 8 squared, it's also 4 cubed. I could take this picture and cut it this way, and also cut it in the halfway to make 4 quarters, and then imagine that those were 4 sheets of paper that you then stacked up, with the top left one maybe on top, and then putting it on top of the next one, on top of the next one, on top of the next one. And you stacked all of these together, and you imagine that that was somehow a 3-dimensional cake, where each of the cubes had been colored gray or red. You could attempt to use the same idea, but just by not measuring how much is in each row, but measuring how much is in each layer. So this is, let me draw something. It's very hard to teach without a chalkboard, actually. That's okay. That's why I bring one with me. Here we go. Okay, chalkboard time. So what we had over there is we had a board which looked like this, and you're imagining that you're cutting it into 4 subboards, which you then stack like this. Does this make sense? He's imagining he stacked them. Now, if I have that, then I imagine that is just one big 3-dimensional cube. And by the way, that 3-dimensional cube looks sort of like this. Does it make sense what I'm doing? So it's like it's got the 4x4 pattern on top, and also it's 4 tall. Oops, those lines don't quite line up, but I think you know what I'm getting at. This is like this. So this is what the picture looks like in the end. And then what he's saying is, if I could mentally visualize cutting it, moving it, and then attempting to remember the evenness or oddness of each of the layers, then I could track down exactly where it is. For example, I could try to figure out whether this layer right here is even or odd. And by that layer, I'm referring to everything like this. Did that make sense to people? And if you know that for that layer, that's one thing you remember. You then try to remember for the next layer, whether this layer is even or odd, and that would be all of these. So you use 4 bits to memorize which of those 4 layers, each of those 4 layers being even or odd. Now, at some point, one of the squares gets touched, and so one of those layers changes. So in 4 bits, you're able to track down which of those layers it is. Okay? So that takes 4 bits to find out which layer it's in. But you can imagine cutting this cube in different ways also. It's like if you had a block of cheese and you're slicing it. You can also slice it this way, where the slices are this, 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 and this. So in 4 more slices, 4 more bits, I can tell which of the layers it is this way. I'm just going to draw 4 arrows. 4 more bits tells you which of those 4 layers it's in. If I knew which of these types of layers it's in, and which of these types of layers it's in, if you look at where they intersect on 4 things. How would I figure out which of those 4 it's at? There's actually another set of ways you can cut this. You can also cut this as if those are somehow 4 layers which are stacked in front of each other, if that makes sense. So there are 4 layers which are stacked in front of each other. Right now we've just got this cube, and we've cut it in different layer types. This kind, and this kind, right? So it takes 4 more to figure out the front to backness. I'll put a little 4 here to figure out which of the front to back it is. Altogether, 4 plus 4 plus 4 is 12. So you can actually do this in 12 bits of memory. Okay, so this is exciting because this is something which is actually a fairly technical thing to do it all the way through. I will say, if you keep thinking it this way, it helps. And it turns out at the very end, you find out that there's a technique to do this where you only have to remember 6 bits. So I did the whole thing with remembering only 6 bits of information. And I'm going to jump all the way to that by just showing a technique that you can use to actually figure this out. So, and actually 6 is because it's 2 to the power 6 is 64. There's something nice about this. If you had 6 bits of information, that's actually just the minimal amount you need to identify for which of those squares has changed. So there's a certain limit here. The log base 2 is actually the best you could do. But I'll tell you a bit about the 6 bits that were used, because this is quite fun. This one you don't need to think about any cutting it into any weird things. I'm going to tell you that we started with just some board with 8 by 8, right? And actually, so in a longer talk, I usually let people try to figure this out, but this is a shorter talk, so we don't have that time. The first bit I remember is the number of reds in the bottom half, even or odd. That's a very powerful hint. What's the value of that? Suppose I know in the bottom half of this board whether the number of red squares is even or odd. What does that help me do when I finally get to see what you've done?
That's the problem in that.
It cuts the problem in half, exactly half. Because you see, if I know the bottom half had, I don't know what it was, an odd number of reds. If I knew it had an odd number of reds, then suppose it changed to an even number of reds. Then you'd touch the bottom half. What if it didn't change? Then you touch the top half. I have actually exactly cut my space in two, and they're two equal halves. This is actually explaining how you could hope that you could do this in 6 remembering things. Because if the first remembering thing cuts your possibilities from 64 to either these 32 or those 32, somehow the second thing you remember should be designed so that it also cuts that, in like your 32 spots, into 16 here or 16 there. And then the third thing you remember cuts from 16 possibilities to 8 possibilities. The fourth thing you remember cuts from 8 possibilities to 4 possibilities. Fifth thing you remember cuts from 4 possibilities to 2 possibilities. This is exactly what I was doing, by the way. If you saw, I was narrowing it down. And the sixth one tells you which of those 2 possibilities it is. Now, actually, this technique actually works really well. I'm happy to show you how easy it is to do. This actually can become a parlor trick that a 5th grader could pull off. They might not understand why everything works, but I'm going to explain to you how you can actually do this trick like what you just saw me do. First, I need to know if the bottom half has an even number or odd number of reds. But that's a mess. How do I do this? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've lost count. This is actually highly, highly dangerous to attempt to do. Because as you're very nervous and you're counting, you just count up. And I'll tell you, there's an evolutionary reason for this. Humans were not evolved to say, there are exactly 17 bears running at me. Doesn't matter that there's 17. There are enough bears, just get out of there. Okay? So we're not supposed to count numbers like this down to the number. It was useless. On the other hand, it's very useful for us to say, those aren't bears, those are deer. So we're very good at like visual processing. Okay? So I'm going to tell you how I did this visually. I looked at it for some tips. Actually, the first thing I saw was this thing. Has anyone ever seen a shape like this before in their life? Yes, Tetris. This is the correct generation. Tetris, a state-of-the-art video game that I grew up with. Okay, so Tetris, Tetris shape. This thing, Tetris shape. Let me go back to my board. Tetris. Does anyone know why Tetris is called Tetris?
There are 4 squares in each.
Oh, because that means 4. Okay, so now there's something nice if I care about whether there's an even or odd number of red things. If I see somewhere, that there are 4 red things, I could imagine that I rip that out of the picture. And the number of red things at the bottom, even or odd, does not change. Right? So if I care about I don't care how many reds in the bottom half, I care if it's even or if it's odd. Let me imagine that that is gone. The even and odd won't change because I reduced by 4, which is an even number. Okay? Next thing I looked at this, I said, I see a shape here, and I see another shape there that's upside down and looks exactly like it. There's something nice in mathematics. X plus x, if x happens to be an integer, a whole number, x plus x is always even. Well, of course, because it's like you could match them up, right? Even means that you could match up things. Okay, so I take these two and I collide them, and they're gone. They vanish from sight. And the number of the evenness or oddness of red stuff in the bottom does not change. So this thing, Tetris, is gone. That thing collided. I have 3 left. Okay, that's odd. Did that make sense to people? Actually, it's even a story. I told you the story. You can check the story. The story is called Tetris piece goes away, those 2 smash into each other, and there's 3 left. Actually, sometimes you say these 2 just collide, and it's gone. It's 1 left. Odd. Done. I also have a proof. This is more powerful than saying 1, 2, 3, 4, 5, 6, 7, 8, 9, and doing it, like counting 3 times and hoping you counted right and trying to use the majority. This is a proof. That's the value of learning how to prove things. A proof is a very short sentence you can say that you can replay and be 100% sure that it's correct. Okay? Great, so the bottom half is odd. Let me write that down. Let me go back here. Even or odd number of reds, I'm going to erase this. Oops, I'm going to erase this part. And I'm just going to write that the bottom half was odd. Okay, I'm going to do two things. I'm going to write that it was odd. I'm also going to write a 1. So in mathematics, sometimes actually anyone here who's taking concepts of math, any of the students here who are taking concepts of math are learning about this kind of thing right now. You can also write down things like the remainder when I divide by 2. This is a concept called modular arithmetic. So I wrote a 1 because the number of red squares in the bottom half, if I divide by 2, has a remainder of 1. 1 just means odd. Okay. Next thing. The next thing that I remembered, I have 6 bits I need to remember. The next one, well, let's be consistent with colors. So the next one, I actually cut it this way. I remembered in total between these two areas is the number of red squares even or odd. This picture means in total among those two areas. Not how many reds are red on the top part and how many reds on the bottom part. It's the total as if I added together. Let me first calculate it, and then let's explain why this is so powerful. How do we do this? We look at this and we try the same game. Okay, so now I'm looking at rows 3 and 4. When I look at rows 3 and 4, I see in rows 3 and 4, there's another, like an x plus x. There's 2 vertical things, which are 2. I don't know if you see what I'm talking about. Rows 3 and 4, and then here, there are 2 red things, which are here. Bam, they're gone. Okay? Then I take that piece over there, and I stick it over there, and it's a Tetris piece. I just moved it into there. It's a Tetris piece. That little red square got moved into that spot, got a nice square Tetris piece. Those are some of our favorite kinds. Gone. Actually, that entire 3rd and 4th row has vanished. I care about the evenness or oddness of red stuff. Go down here. Well, that Tetris piece is gone. That's gone. This one I actually see, I mean, when I looked at this, I was like, okay, well, these two things collide with each other. I'm leaving that one. It's odd. I can actually replay this. 3rd and 4th rows, those 2 red things collide. That one goes there. That one's Tetris piece is gone. That's gone. And then over here, like, those collide. 1. Okay, so it's 1 left. 1. 1 means odd. At this point, I want to take a step back and say, why are these useful? Why is it useful to study that thing and then the other thing? It's because you see from the first thing, what does the first thing tell me? You know, at some point, this our volunteer actually changed one of the squares. Our volunteer changed this square. So if what you were doing was this, then you would have noticed in the first memory piece that the bottom half changed in its evenness or oddness. So I would have known it's in the bottom half, which is sort of like what I told you. I told you it's in the bottom half. Now the second thing that happened, our volunteer's square was here, and the second piece would have detected that whatever the volunteer changed, it's inside the shaded region. You see, if in the second piece I noticed no change, I would have said the volunteer's piece is in not the shaded region. But you see, once you already know from the first step already tells you it's somewhere in the bottom half. If you know it's in the bottom half, if you find out it's in the shaded region, it's in the bottom half of the bottom half. If you find out it's in not the shaded region, it's in the top half of the bottom half. You see, you've split into exactly half your possibilities. The value of this way of doing things is you always cut in exactly half what you had before. What's the next one? The next one, if I want to continue this pattern, remember it's an 8 by 8. What I do is I need to know evenness or oddness of red squares in this region. So these are like the rows number 2, 4, 6, and 8. Now let's do it. Rows number 2, 4, 6, and 8. All right. Okay, row 2, that's sort of 4 reds. Okay, nothing there. Oh yeah, and I do something like this to remember. It's like bees doing a dance. You do something you remember better. Then over here, that's very nice. There's like alternating. But somehow there's 4 reds, so there's still nothing there. Here, there's still nothing there. And over here, I see somehow a number of reds is 1 extra. Okay, so it's 1. 1. Next. And by the way, if you knew that, you would already have traced down to exactly which row was touched, if you can remember those three things. Next, what do you think is a good thing to do next? Yes, vertical. Take the right half. How much redness is, even or oddness of red, is in the right half? Because if you have tracked down which row it's in, now you just need to know, is it in the shaded part of that row, which is the right half of it, or is it in the not shaded part of the row, which is the left half of it? So let's do the right half. Okay, so then I come over here, and oh, this is great. These two things are x plus x. There's a collision that happens here. These are gone. If I look at what's happening up there, I somehow wanted to take that little lone red square and stick it up there to make Tetris piece. So I got the square Tetris piece, so that's gone. And then somehow there's like two things and two things, but those are all even. If you can see, it's just, this is even. This collision, that thing flew up there, made a Tetris piece, it's gone. Those two things are even. So it's even, 0. Okay. So this is 0. I promise you this will be worth it. There's a punchline at the end. So, okay, let's do all of this. Now the next one is these. Red squares over there. Let's see. Okay, now we're here. What's the best way to do this? I think maybe what I did is I took that top one, I tipped it over to the right, and I got the nice 4 long Tetris piece. So that ejected. These things collided with each other. There was one left. So I stick my finger up because I can't remember anything. I'm a mathematician. I chose to do math because it was the easiest subject. You don't have to remember anything. All you have to do is think. This is actually true. This is true. And this is how I remember that there's an extra 1 from here. I count on my fingers. Now let's go over here. And over here, oh, what's an efficient way to do this? Maybe I will take these 3 and smash them into these 3. Now that's all gone. There's just 2 things left. They crash into each other. They're gone. It's all gone. Oh, but there's still a 1 here. That means that it's 1. It's odd. Okay? 1. Next, the last piece. And by now you can guess what this is going to be. This is going to be columns 2, 4, 6, and 8. This is my picture. Hopefully it's understandable. 2, 4, 6, and 8. Columns 2, 4, 6, and 8. Let's just finish this up. So column 2, I just somehow see 4. This is the hardest thing. You have to actually kind of count. So this is 4. So that's nothing there. This thing here, I'm going to count the grays. This column, the grays, give me 1. Okay. Now over here, the grays are easy to count. That's even, so nothing happens. And over here, it's like, oh, nothing happens. So it's still 1. Okay. So what I claim is if, in your head, you can remember 1, 1, 1, 0, 1, 1. If you can remember that, that's all you need to remember to solve this problem. Because then when you go and see what he does after he touches it, you just use this to backtrack and figure out exactly where it is. That is how you can actually do this, remembering 6 bits. These are the only 6 bits you need to remember. This is how you can efficiently calculate those. There's only one problem. It is very easy to make a mistake. Because if you're going to do this, you have to remember, okay, it was 1, 1, 1, 0, 1, 1. And now he did this, so is it in the shaded part or not shaded part? Or what just happened? You can easily flip yourself over in the knots. And this doesn't have any robustness in the sense that once you make a mistake, you're just off in the wrong territory. So now you might wonder, what is the weird thing that I did? I did this. Why did I change this to red? Well, if I change it to red, let's pretend. So that's not what really happened. What really happened is that first, he changed this, and then I changed that. That's what happened. But in my head, I imagined that as soon as I saw all of this, I changed this. Then I wasn't looking, and he changed that. Do you see that it's exactly the same? So again, let me replay this. What you guys saw is that he changed this, and then I changed this. What I saw in my head was, I intend to change this square. And I'm not watching, and he changes that. But they're the same. What I'm showing is that it's called commutativity. Addition is commutative in a certain sense. When I closed my eyes, resolved that I would change this square no matter what when I got to see it again. Which is the same thing. It's like what is it, like deficit spending or something, right? It's like I knew I was going to touch this, so it doesn't matter that he touched this first. It would be the same picture. What would have happened if, for some weird coincidence, which has a 1/64 probability, what if I had resolved to touch this and he also touched it? Then you would have watched this, and then I would do this. In my head, I would have said, I'm going to do that, I'm not watching, and he touches that. It's the same. So now why do I care so much about changing this square? Suppose I change this square. Suppose I got my way. Like suppose I got to have a different game. The different game was called, you make whatever mess you want, I get to change one square of my choice. After I change that square, what happens to all these calculations? Let's go back up to this thing. If I got to change that square, what's the sum of the reds in the bottom half? It's actually 0. The reason it's 0 is because it was 1 before. But if I changed my square, I need a color. How about here? If I changed my square, it wouldn't be 1 after all. This thing would turn into 0. So by choosing that particular square to change, I would have had to deal with the 0 there. Actually, how about the second one? This is the magic square that I was trying to change. If I got to change that, if the game was, you make a mess, I get to change any square I want that square. If I change that square, the even or oddness of red things in the bottom half, not bottom half, in the second picture is also 0. Because that square happens to be in the shaded part. The way to think of this is that when you're counting stuff happening in the shaded part, if you make any change in there, it flips the even or oddness. How about the third picture? Also there. So that actually means that in my version of the world, it was actually 0. How about this one? Now there, even if I got to change that square, the evenness or oddness in the right half would actually not change. Because it's not in the shaded part. So that would stay 0. This thing would change. And this thing would change. Do you see what I actually have to deal with? All zeros. That's extremely convenient. So basically, I am able to know that if I touch this, then I'm actually playing a fresh game. The fresh game is called pretend that everything was zeros, and then figure out what he changed. You see, because the game was originally figure out which one he changed. But if I had to remember, my state of affairs is there's like some evenness or oddness on all these areas, and I don't remember, was it 0 or was it 1? It's very hard to execute the trick. Instead, what I said is, if I just remember to whack that square, I don't have to care about anything else anymore, because when I open my eyes, I will be staring at a game board where it was reset to zeros, except that he changed one of those squares. And now I just replay backwards all of these steps. So this is the most technically advanced piece of this trick. I will say that somehow that's like a non-trivial leap. So I'm sorry if I lost some of the people here. This is actually a pretty advanced topic. But this is actually a pretty advanced topic. However, the main thing to get out of this is that somehow very complicated things can turn into quite simple things. And in fact, even the way that I went to figure out what was going on afterwards, maybe I'll just show you how I decoded it at the end. It was like I knew in my head I was going to touch that square. So then after I touched that square, here's what happened. Everyone was looking at this. This is what the state of the affairs of the world was at this stage. And in my head, everything had zeroed out. So what I meant is that in my head, if nobody had done anything else, the number of red squares in the bottom half is supposed to be even, because it went to 0. So then what's the first thing I did? I went and looked at this, and I said, bottom half, is it even or odd? Smash those two together. That's a Tetris piece, it's gone. I'll just smash those two together. Oh, there's one left. It's odd. That means the bottom half is odd, but it was supposed to be even. I specifically touched this to reset it to even. Does this make sense? So now I know that you touch the bottom half. And the next thing I did is I said, okay, Let me check row 3, 4, row 7, 8. Row 3, 4, these two red things smash together, that thing goes there, it's a Tetris piece, it's gone. Down over here, Tetris piece is gone, that piece is gone. Oh, this is this thing, put these together, it's odd. Wait, but it was supposed to be even, because I reset it on purpose. Since it was supposed to be even, I know that it was in the bottom half, so it has to be whatever overlaps with that, which is these two. And it just went on and on and on, because it's so easy for me just to say it was supposed to be even. So that's actually what was going on. The even better part is how did I even calculate this? So does this sort of make sense? To figure out exactly where it is, it's this process of elimination at the end. And the last really fun part is that, actually, how to calculate that I should touch the square in the first place. The way to calculate that I should touch the square in the first place is to go back to the picture we had before. There's a certain property of the white square, of the white dot. The white dot is such that wherever there's a 1 in the red, in this purple color, wherever there's a 1 in this purplish color, the white dot needs to be in the blue part of that. Because I'm trying to flip all of the 1s to 0s. So I'm specifically saying, here is a chessboard. I need to choose one square to focus on, where it happens to be in the blue part for any time that I have a purple 1, and it has to be not in the blue part whenever I have a purple 0. So the first thing I do is I go and actually look at the bottom half. That's the first thing I calculated. And when I calculated that bottom half, I went and looked at the chessboard. I found out that the bottom half was odd. That's how I knew that whatever I have to touch, whatever white square I have to touch, it's in the bottom half. What I'm showing you is actually the encoding algorithm is precisely the same algorithm as the decoding algorithm. I actually only practiced one task. It's a fun thing. The function is actually the same function, both encoding and decoding. I only had to practice one thing. The thing was called stare at picture. Count bottom half. Is it even or odd? If the bottom half is even, then I will have to do something with the top half. Focus all my attention on the top half, because that's where the white thing I'm going to touch is going to be. If the bottom half is odd, then focus all your attention on the bottom half. And that's where I'm going to touch a white square. Those are the exact same words I just said when it came to what did you touch. And like if you see how this is going, it's exactly the same algorithm running all the way through. So I did actually the same thing twice. And in the end, that's how this trick got pulled off. If this is explained slowly to a 5th grader, they could actually do it. They just would have to know, algorithm is like, these are the spots. If you find an even number, focus on the first half of it. If you find an odd number, focus on the second half of it. Do this, and eventually, at the beginning of the game, you focus on one square. Remember that one square's location and close your eyes. When you get to see again, touch that square, and then do the exact thing that you just did. If you look at the bottom half, if it's even or odd, focus your attention on the bottom half or the top half of it. Do. At some point, you're focused all your attention on one square. That's the one you touched. So the same thing twice. So I came up with this because for some time, I was actually trying to find ways that you could do like a mathematical performance, like at a museum or whatnot, to show people like, this math is quite powerful. But the origin for this question was actually in the Putnam class here at Carnegie Mellon, where one student told me an idea. It wasn't exactly this, but told me an idea that eventually we could turn into this. So thank you. So we have about 4 minutes. If people have some random questions that you'd like to ask, I apologize. I should have left more time. I usually want to leave more time when they're parents. But if anyone has any random questions, I'm happy to answer them. It doesn't have to be about this talk that we just had. Yeah.
Just curiosity on the Putnam, what was the max score that you ever saw?
Max score that I ever saw? Well, there was one year that Carnegie Mellon won the whole thing. And in fact, when it won the whole thing, the people on the team were all in the top 5 in the country. And the maximum score, I don't know, it was like probably over 100. Yeah, which is like 10 questions. But again, it doesn't really matter. I mean, what I should say is, you can see I didn't commit this to memory. And that's because I don't care so much about scores or even winning. It's somehow about the experience, right? And so I feel that we just want people to go through this, learn, think about interesting ways to think. Whatever score they get, it's like, sure. Yeah. Sure, and you had a question too, I think.
Oh, I was wondering if that 6-digit number was like a code for which square you
It is. It is. If you number the squares from 0 to 63 in base 2, that's the exact location. That's actually how I came up with it. I came up with it that way, and then I said I can't do that in public, writing down like all this stuff. It does not look impressive if you do the trick with a pad of paper. It looks much more impressive if you can do the whole thing visually. So that's what happened. Yeah. Yeah. Any other questions?
You said that Carnegie Mellon was number 2 this year, and
Oh, they're always the second most in the top 500. So there are different ways of counting the ranking, right? So somehow there's an official ranking which is based on 3 people. So somehow that's how they make it fair, because if Carnegie Mellon has 200 people play and some other school has 10 people play, they want to somehow find some even way to measure it. It's sort of like how if you have a city's football team, the football team in a larger city is not allowed to put 30 people on the field at the same time. You have to put the same number of people on the field, right? But anyone who wants to play can play, right? So the deal is, officially, based on the top 3, we have some rank, whatever. What I care much more about is the secondary measure of how many people are in the top 500, because that anyone is allowed to try. And we have been in the second most among all US universities and Canadian universities for like 5 or 6 years. I lost count. We don't bother to count anymore. Yeah. Okay, well, in that case, thank you all for your time.